Hi guys, this is question number 30. The following data was collected for the rate of disappearance of NO, as in nitrogen monoxide, in the reaction of 2NO plus O2 yields 2NO2. Okay, so here we have three experiments, and they started with different concentrations. Notice I have NO up here on the top here, O2, those are the two reactants, and then the initial rate is listed for us. Notice, and here's the important part, notice that some of these experiments were started off with similar concentrations, such as NO and NO are both the same for experiments 2 and 3, and O2 is the same for experiments 1 and 3. So we're going to use those different concentrations to help explain or to figure out what the order is. And the only way you can find the order is through experimentation, through a list, a table like this, where you have different concentrations and some of them are the same. So let's take a look at what we can do. My goal is to find the order. I'm going to find the order for O2 first, and here's how I'm going to do that. I'm going to take a look at experiments 3 and 2, because that's where NO is the same, and I'm going to see in 2 and 3, I'm going to see O2 change. I'm going to see how that relates to the rate on the other side. Okay, so here's what it looks like. If I take the concentration for NO in experiments 3 and 2, or I should do 2 and 3, it doesn't matter. Like this, it's going to be, take a look at the concentration for NO. It is 252, like that, and I'm going to divide them. Experiments 2 and 3, 252. Notice that these cancel because they equal 1, so that's no big deal. And this is experiment 2 and experiment 3. And what does it look like for O2? Well, for O2 with experiment 2, I get 0.0250, and I divide that by 0.0125. Notice that experiment 3 is exactly half of the concentration of 2. That means I can simplify this to 2 over 1. Okay, now that all equals, now take a look at this. Experiment 2 is, you know what I'm going to do here? I'm going to move the decimal point one place to the right so that I get 11.3 times 10 to the negative 2. The reason why I did that was so that I have negative 2 and negative 2 for both of those. So now I can just take a look at the numbers and forget about the times 10, because I'm going to divide them. So for experiment number 2, I get 11.3 on top, and experiment number 3, I get 5.64 on the bottom. Notice for the rate that when I double the concentration for O2, the rate doubles also. 11.3 is exactly twice the 5.64. So because I have a situation that looks like this, okay, I didn't just make this up. This is written in the book. You can see it. I'll tell you what the example problem is in a second, so you can follow through the example problem. But for my reaction order, this is my reaction order variable, and I'm not sure what it is until I compare. I have to get NO out of the way, which I did by using two experiments where they're the same concentration, and then I used experiments 2 and 3, so 2 was double the concentration of 3 for O2, the 0.0250, over the 0.0125, and then that is to some order, and in this case, if I put a 1 in for n, that makes this equation correct. So if I put a 1 in for n, that means 2 over 1 to the first power equals 2 over 1 for the rate, which is correct. So that means that as I write my rate expression, that I know what one of them is already. Now I have to find O2, or NO is what I'm looking for. So I got K, yikes, here we go, NO, and I'm not sure what this one is, that's an M, but I do know what O2 is. And O2 is 1, like that. So let's find NO then, and I'm going to do that in green. So what I'm going to do to find NO is I'm going to use two experiments where O2 is the same. So that means that I'm going to use experiment number 1 and number 3. And the reason why I do that is because O2 is the same for both of those, which means that I can just get rid of it and ignore it like I did for the first one, for NO. So take a look at what I have here. I have for 1 and 3, I'm going to put 3 on top because it's a larger number. So for NO, here's what I'm going to do. I'm going to do experiment 3 over experiment 1, which means that I have concentration 0.0252, like this, divided by concentration 0.0126, like that. Okay? Now all of this, like I said before, is going to be to some order. Let's see what it does for the rate. So what's the rate? The rate for this, and I need to get rid of this stuff here so you can see it, is, now take a look, I got that rate and that rate. So experiment 3 is 5.64, and as long as these two are the same when I'm dividing, it doesn't matter. So 5.64 over 1.41, like that. Now what number do I get when I take 5.64 divided by 1.41? So what I get then is number 4. But here I have 2, because 0.0252 is twice of 126. So what number for M would make this case? Here, I'm going to scroll up a little bit to give myself a little bit more room so you can see what's going on. There we go. Now I don't have to force it all in one thing here. So that equals 4 for this one. This one here equals 2, so I get 2m equals 4. Well, what does m equal then? Now m is going to be a low whole number, like 1, 2, or 3, and even 0. Okay? So clearly, the one I would pick then would be 2, because 2 squared equals 4. So that means that now I've found my order for NO, and there's my reaction. So what's the rate law for this reaction? I just found it. Rate equals K. Now the question is, what are the units for the rate constant? So rate equals K times the concentration of NO squared times the concentration of O2 to the first. What are the units for the rate constant? That's easy. Always, we should get used to writing this down because this is a very common question. So that's going to be the rate divided by NO squared O2 to the first. That means, now I didn't even check to see what, I have to scroll up for a second to see molarity per second. So molarity per second for the rate, and molarity squared times molarity. So we get rid of that, flip seconds to the bottom, and what I get, what I'm left with then is molarity to the -2, seconds to -1. That's the units for a rate constant. All right. Stay tuned for part 4.